So thank you very much. So I'm here to present SYgraph. We call SYgraph because it comes from SYCL, and this is a joint work from with Antonio De Caro, my PhD student, who just presented this work a few days ago in a conference, so he didn't make in time to come today, and Professor Gennaro Cordasco, a colleague of us here in Salerno. So the work I'm presenting is a portable heterogeneous graph analytics framework for GPU. I will show you a brief introduction, the background about graph analytics, how do they work on the GPU, and later, I will show you the SYgraph, okay, the SYgraph API. So the contribution is actually the API, distribution model, and a new algorithm, which is actually a new data layout, which is called Two-Layer Bitmap. And this one will allow us to have higher performance. And at the end, I will show you experimental evaluation. This work works on GPU from all the vendor, Intel, AMD, NVIDIA. So we are proud of this. So this is a very portable framework. And here we go with the introduction. So graph analytics. So well, graph are really everywhere nowadays. So we have graph. We need to use graph for modeling social network. You know, if you want the follower graph, we need graph if we want to analyze the web and hyperlinks on the web. So for crawling, ranking, we need graph if you want to analyze biological networks. So those graphs, specifically, if you think about the graph on social network or hyperlink or those are very huge. So million of nodes, billion of edges. So we need computational power. And here we have GPUs with many cores that can help on doing the processing. So the idea of this work is to use the GPU to do graph processing. We are not the first one. And indeed, it's a very hard challenge. Why? Because, well, GPU, I mean, graph workloads are not really well suited for GPU. So the GPU likes collapsed memory access, but unfortunately, you don't have, you don't have this collapsed memory access on the GPU. If you think about the graph, you may have you may have a skewed degree distribution, which means that some edge may have only a few neighbors. Some vertex can have a few neighbors. Another one can have many neighbors, and this will lead to unbalance. Will lead also to a lot of load imbalancing and thread divergence. This is not good for the GPU. The topology itself is irregular, so we have many unpredictable memory access. Unpredictable memory access are not good for GPU either. And another problem is that this is a typically memory bounded problem. Okay, so and it's very easy to write an algorithm that underutilize the GPU computational power. So in fact, was classically was an algorithm that was much faster on the CPU. Only recently we start to have efficient GPU implementation. It's not easy. When we go on the GPU, the approach we follow, this is the approach we follow in our work, is to think about to design graph algorithms in terms of frontier-based processing. Frontier-based processing means that we have a frontier. This frontier represents a list of active nodes, and then we apply some logic on these nodes depending on the algorithm, and then we prepare to the next iteration. In this way, we make graph processing an iterative algorithm on each iteration we work on a larger or smaller set of vertex, which is indeed the frontier. So this is an example. In this picture, you see a BFS algorithm. So how does it work? So this breadth first search algorithm. So step one, you only have a vertex 0 in the frontier. Step 2, you move to vertex 1 and 2. Step 3, your frontier only has vertex 3, 4, and 5. Okay, this is a good approach to parallelize on the GPU. In general, to parallelize graph algorithms, specifically for the GPU, this is very good. Um, how do we represent frontier on our GPUs? So there are two ways to do the job. So at least if we look at the state of the art, there are two ways to do the job. One is called vector-based frontier, where each node, each entry represent in our vector frontier represent a node. Okay. Another approach is a bitmap-based frontier, where practically you have a bitmap where each bit is either 0 or 1, whether the bit I represent whether the vertex I is in the frontier. So if it's 1, is it on the frontier? If it is 0, it is not. So uh, those are two commonly used representation. There are pros and cons for both representation. Bitmap Frontier have some very good feature for the GPUs. First of all, you do not need to handle duplication because on a classical vector frontier, you may have duplicated index. This does not happen in a bitmap frontier. And they also tend to be more compact. You can squeeze a lot your data. There are also cons. If you have a lot of sparse data, it may end up you to have a lot of data in your bitmap. But overall, this is much better for the GPU. So this is one of the approach we follow in our work. And looking at the state of the art in terms of GPU graph framework, I mean, we have GPU from high-end GPU, no, from Intel, the one you find in Aurora, Argonne, from NVIDIA, many cluster AMD, like here in Europe, we have Lumi, which is a AMD cluster. And, we have love level API for them, like level 0, CUDA, and Rockum. And if we look at the framework available right now, so most of them are research work, but we also have CUGRAPH, which is made from NVIDIA. They can only target NVIDIA, and they are not portable. So this is a big problem because we like portable standard, and our proposal, actually, our contribution goes on three directions. First one is to design SYgraph as a first portable heterogeneous graph analytics GPU framework. It is based on SYCL, so it is portable because based on SYCL, and of course on C++20. It has a execution model with load balancing, which is very good for graph traversal, and very interesting. It also presents a new memory optimization, which we call two-layer bitmap frontier. This is very good because this allows us to be even faster than state-of-the-art framework based on CUDA. So I will briefly show you those three contributions, starting from the SYgraph API. The idea of the API is the following. We want an API that allows us to model all the existing algorithms. So if we think about this iterative approach, the idea is that we have three primitives: the advanced, the compute, and the filter. So advanced means that we explore the neighborhood of our frontier. So then we identify the node of the next iteration frontier. And it's mostly an edge operation. And this is the advanced operation. Then we have the compute. So once you know which node are in your frontier, what do you do with them? So in the compute, we can do different things depending on what algorithm we are doing. If we are doing a BFS, we can update the distance vector. And finally, in the filter, we decide which node we keep from the next iteration in the frontier. So typically we remove some node in the frontier. So and we progress on our algorithm. So if you think about that, all algorithm can be defined around those three primitives. And so we have an API that allow you to do this. So this is a BFS algorithm, the code you see here on the right. This is a SYgraph code. So you have a BFS takes as an input a graph, an array of distances, and the source vertex. We have the green API you see, like make frontier or insert, are API that allow you to play with the set of nodes of vertex in the frontier. So to make the frontier, you make two frontier because it works like double buffering. Now you have an in frontier and an output frontier for each step. Then you'd have this iterative code in line 8, which you repeat those steps until the frontier is empty. And what you do is to practically define two operations. The advanced operation, on which practically you choose practically this is a lambda function. Okay, so if you know SYCL, you are familiar with that. So actually, this code in this lambda will be executed on the GPU, and this lambda returns true if the newly discovered vertex must be kept in the frontier, or false if you have to discard it. And typically in this code, the one you see is false only if you already visited this node. Then on the execute, in this case, you have to update the distance vectors. And then at the end of the algorithm, you swap the in and the output buffer, and you repeat this for each step. This simple code is a BFS, okay? And this is how the BFS work on SYgraph, and it works on all the algorithms because this is actually SYCL code. Actually, the frontier and the execute go on the GPU, while the rest goes on the CPU. The execution model is the second contribution of this work, and the idea of the execution model is actually that we have the SYCL execution model, which applies to our model. We have workgroup, subgroup, and thread, and actually, practically, in what you see in the first iteration, each workgroup is assigned to a specific integer, and while the subgroup processes different region of that integer. This is the overall idea, and initially, so practically, we have each thread assigned to each bit. Why? Because in SYCL, we have this group algorithm that allow you to form, for instance, a very fast scan operation within a subgroup, and the subgroup here match with the size of the integer, and this allows to have threads cooperatively process each vertex neighborhood in parallel. This is a low-level optimization, but this to show you that we exploit SYCL 2020 group algorithm. Then when we move to the next step, then the lambda will apply the algorithm when you do the execute. We do this for all the thread. This step of the algorithm is it's easier. The first one is more expensive. We have a number of problems we had in this, and this is some of the solution we found out. First of all, what happens if you only if you have only one bit set to one? Well, practically what we try to do is to adapt the integer size to the size of the subgroup, which means that if you are on NVIDIA, the integer is 32-bit. If you are on AMD, because on AMD a subgroup is mapped into a wavefront which has 64 thread, we use 64-bit integer. So our is a virtual integer. And on Intel GPU are programmable subgroup size, so you can tune it. So Intel GPU is more flexible for this kind of algorithm. We also applied thread coarsening to improve GPU resource utilization. This is well-known optimization, very similar to loop paralleling applied to parallel 4. And in the end, we also have this two-layer bitmap optimization. The idea of the two-layer bitmap is that what happens if you have many zeros on the same integer? Well, we use a trick. We had one second layer of bitmap that if there is a zero on the second layer, this will allow us to skip a whole integer in the first layer, okay? In this way, we can handle much better the sparsity of the dataset. And this is another novelty that no one did it before. This allows us also to be faster than existing framework like cuGraph. Allow me to show some number because we did a lot of experimentation. We compared against the state-of-the-art research work, which are Gunrock, Tiger, and SYgraph. Very important, some of those frameworks require pre-processing while we do not. And we tested this on different datasets of different sites. For instance, the largest one is the Twitter dataset, which has 21 million nodes and 530 million of edges. Experimental evaluation, I will show you some results. Then at the end of the talk, I will show you the paper where you can find more results. Here is BFS and single source shortest path. And practically here you can see both the time, for instance, for SYgraph, which is a framework which has preprocessing, with and without preprocessing. And we are always better if we consider the preprocessing. In some cases, we are better even without the preprocessing. So this is because we have very good memory utilization. And this is against state-of-the-art framework. Here there are two more algorithms. These are a little bit more expensive. One is between centrality, the other one is connected components labeling. Also here, we are much better. The state of the art, if some line is missing, is because state of the art was not running on this dataset. We can run everywhere. Why we are better? Well, we profile the memory footprint. Those are iterative algorithms. So we profile the memory footprint during the iteration. And here you can see some dataset have run for 640 iteration, others for just 10 iteration. But in all the case, we have a lower memory footprint because we have a much more dense representation of our graph representation. Um, uh, I have more results because this is a direct comparison against Google Graph. Google Graph is not really state of the art, but it's made from NVIDIA, and we run it. We compare also Galois, which is a CPU-based implementation of the same algorithm. In this case, we are much faster, at least twice faster, depending on the dataset. I want to conclude to show some number regarding portability. Here we have three GPUs, let's say from the same generation. We have Intel Max 1100, which we run it both with SYCL with level 0 backend and with SYCL with OpenCL backend. An AMD MI100 with Roggen backend, and NVIDIA B100S with CUDA backend. In this case, you can see, uh, let's say AMD and Intel perform much better in this kind of workload. Intel, because the trading model, this programmability of subgroup size is very good for graph algorithm and has better cache. AMD mostly because of the cache. But overall, the good point is we can run the same algorithm everywhere, and we are very good performance everywhere we hold hardware. So our results are performance portable. And this is a very important take, because in this way, we can write our algorithm in SYgraph, and because of SYCL, it would be not only portable, but performance. And to conclude, okay, so this is my last slide. I presented SYgraph, which is a portable graph analytics framework, portable because based on SYCL. It has load balancing. It has a new two-layer bitmap frontier layout that allows to have better, lower memory footprint and therefore better performance. And last note, I want to thank Antonio De Caro. This is huge work by Antonio De Caro, who is contributing currently to oneDAL. So this work is coming in. So we are talking with the oneDAL team, and this work will be integrated into oneDAL as an open source contribution. So you will see this connected to oneDAL interface hopefully soon. So if you have any question, this work has been published at the International Conference on Parallel Processing. So proceedings will be had soon. We already shared the paper online as a preprint, and I can send you the link of the paper if you're curious about results. The code is open source indeed. It's under Apache 2 license. And I'm here for any question if you have any.
Okay, thank you so much for your talk, Biagio. Do we have any questions or in regards to this? I will say that the performance numbers that you were sharing was really interesting in terms of how competitive they are, even compared to NVIDIA H100. That was quite a quite
No,
a
to be honest, this is all hardware, both from Intel and NVIDIA, but let's say it's the same generation hardware. It
yeah.
runs also on H100, but here we had a V100S, and we also had an Intel Max 1100.
Okay.
Let's
Let me
say
let me
GPU from
ask
the
you,
same.
on this particular slide, you said that uh, the Intel Max 1100 performs well on sparse workload and sparse graph, and then but the AMD MI100 excels on dense workloads. Is that something like you could split between if you had a heterogeneous environment where you had Intel Max 1100 and AMD M1i 100, you could like theoretically push one to the other depending on what platform you had. Is that a thing?
Yeah,
Maybe I'm asking
you
with
do
some
both.
kind of certain amount of naivety.
No, of course, you can do it. You pay for data movement. Data movement is very expensive in this case.
Yeah, yeah,
But in the end, it's very interesting because this is a case where NVIDIA GPU perform not so well with respect to the competitors.
yeah.
And the Intel trading model, we also tested more sparse algorithms like graph isomorphism. This is even more extreme. So you see Intel GPU performing much better because of the trading model. AMD pays for the very large wavefront, so the subsides, but recovers a little bit because of the cache. And we have a lot of data, and we had this in the paper. Of course, the technical discussion is very long. But in general, this is a kind of workload where the CUDA NVIDIA architecture is not really optimized for this. It's more optimized on tensor, dense tensor, and not on sparse data. Here we're talking about sparse data where the cache really matters.